All right, so let's talk about how we would interpret and understand what is going on if we were just given the graph initially. So we're going to imagine instead of knowing anything about whether this was a mass spring system or a pendulum system or a gravitational system or whatever, we just had this graph. How would we interpret that? And so one thing is that the graph itself just tells us what the potential energy of the system would be if we could get the system to that position. The mass spring system, for example, isn't necessarily going to get to every single position it could theoretically get to. So theoretically, it can get as far as the spring can stretch and as much as it can compress. But for any given time where it's oscillating, it's only going to move in a certain range of that based on how hard and how hard we push the block in the first place and how much energy we give it. And you could either think of that as, or there's two different ways we could do it. So either it could be based on what position we initially retract it to and then release it from. So we could sort of start it over in this position. Or we could just like smack it, right? So like if we just hit it and gave it a bunch of kinetic energy, we could actually start it in this position, moving to the left, and then it would continue oscillating like we showed before. But in either case, whether we are stretching it back to a certain point and releasing it from rest or smacking it and giving it some kinetic energy, there's a certain amount of work, a certain amount of energy we have given the system, and that is going to define how much mechanical energy the system has. And so one thing that needs to be on the graph in order for us to interpret it is some indication of how much mechanical energy the system has. And so that is what this line here shows. The mechanical energy is this dashed line, so whatever energy values, this is crossing our energy axis, whatever number this is at, that's how many joules of mechanical energy we have available. And we know the total mechanical energy is just the sum of the kinetic energy and the potential energy. All right, so knowing that that's how much mechanical energy we have, the question, remember, we were trying to figure out what happens if the object starts at position -2. So if we know the position starts at, if we know we start at position -2, and we know, so we follow that up to see where that is on our potential energy graph, we can see that that is where our potential energy and our mechanical energy cross. So that means that we only have a certain amount of available mechanical energy, and our potential energy is the same as that amount of energy. And so that means where we are starting, our potential energy has to be, our mechanical energy has to be all potential energy, because our potential energy is equal to the mechanical energy, so the kinetic energy has to be 0, because the kinetic energy plus the potential has to be mechanical energy. It has to be the mechanical energy. And so if the kinetic energy is 0, the object starts at rest. Which you'll notice is exactly what happened when we described how we originally started this. We pulled the object back to here and we released it from rest. We don't know that it's a mass spring system, but we can tell from the graph that it has to be starting at rest, because if this is how much energy it has available, the mechanical energy, and that's how much potential energy it has, it can't have any kinetic energy. It has to be at rest. So then the next question is, what does it do? Does it stay at rest or does it start moving? So we need to figure out the force. Is there a force acting on it? And what direction is it? And that is where the slope comes into play. We know that the force is the opposite of the slope of our graph. And so at this point, we have a negative slope, which means that the force has to be positive, because remember, the force is the opposite of our slope. And so here, since we have a negative slope, the force is positive, and so the object is going to start moving to the right in the positive direction, which, remember, is exactly what happened in our mass spring system. And so we can see that just from the graph. So we're going to start moving to the right. Then, as we move to the right, now we get to position -1. So at this point, we only have this much potential energy, but we have this much mechanical energy, which means whatever our total energy, our mechanical energy is that isn't potential energy, has to be kinetic energy. And so if we subtract these two, whatever this space in between, that has to be the kinetic energy. And if we have kinetic energy, that means it has to be moving. So the object is moving in the positive direction. When it hits this point, our potential energy is less than the mechanical energy, so some of it has to be kinetic energy, which makes sense because it's moving in the positive direction. And here, so we just show the kinetic energy is the total energy minus the potential energy, right? Because all the energy has to add up to the mechanical energy. If you've only got this much potential energy, whatever's left has to be your kinetic energy. So at this point, we know it is moving. And it was moving to the right, and it's moving at a speed defined by this kinetic energy. And if we look at, well, what's it going to do after that? So does it keep moving to the right? Does it get faster? Does it get slower? Does it move at a constant velocity to the right? Well, we look at the slope again to figure out what the force is. Slope is still negative, which means the force is still positive. So it's moving in the positive direction. It's got a positive force on it, so it's going to get faster. But the slope isn't as steep as it was before. And so it's not going to be accelerating as much as it was before, but it is still going to be getting faster. So we continue moving in the positive direction, and it's speeding up, but it's not accelerating as fast as before. So then we get to here. Now at this point, we can see our potential energy is 0, but we still have this much mechanical energy. So now all of the energy has to be kinetic energy. So it keeps moving in the positive direction. It reaches this position. Our potential energy is 0, so all of it's kinetic energy. If all of the energy is kinetic energy, that has to be the max speed. And that's what we observed here. In this position, we knew we were at our max speed, and that's what the graph shows us. At this point, the slope is 0, so the force is 0, which is what happened with our mass spring system. But it was moving to the right. We know from interpreting the graph that it was already moving to the right. And so it's not going to stop just because there's no force. Inertia is going to keep causing it to move to the right. But of course, as soon as it starts moving to the right, now the slope gets positive. Which means the force is going to be negative. And so although it doesn't start slowing down here, as soon as it starts going up this slope, we're going to have a force to the left in the negative direction while it's moving in the positive direction, so it's going to start slowing down. So by the time it gets to this next point, it's going to have slowed down some, which makes sense because we see now the kinetic energy is smaller. Because again, the kinetic energy is the difference between the mechanical energy line and the amount of potential energy we have at that point. So we know we're moving in the positive direction. We can tell we're still moving because we still have kinetic energy. Our slope is more positive, though, which means we have a bigger negative force, so it's going to start slowing down even faster. So we keep moving in the positive direction. Our potential energy is still less than the mechanical energy, so we've still got some kinetic energy. It's just less than it was before. Slope's positive, so the force is negative. Object keeps slowing down. And then eventually it keeps slowing down until we get to the point where it eventually stops. And we can tell where it stops because at this point, the potential energy is the same as the mechanical energy. It has lost all of its kinetic energy and gained all potential energy. And when it gets to this point, it has to stop. So when it reaches point x equals 2, the potential energy is the mechanical energy. So all of the energy is potential. None of it can be kinetic. And so the object is stopped. So the object comes to rest. But now the slope's positive, which means the force is negative, and so it's going to get pushed to the left, and the system is going to repeat itself just in the opposite direction. And so I have this all written out, but it's just doing the exact same thing in the opposite order. We can always tell the kinetic energy based on how far it is between the two parts, the mechanical energy and the potential line. So we're moving to the left. We've got kinetic energy. We know we're still moving to the left because we still have kinetic energy. Our slope is getting smaller, though, and so we still got a negative force because we have a positive slope. So it's going to continue moving to the left and getting faster. Here, once again, we're at our lowest potential energy, which means we have our highest kinetic energy, which means we have to be going at our absolute fastest. And then as our slope starts to get negative, that means the force is going to be positive. Since it was moving in the negative direction with a positive force, it's going to start slowing down. And we can see that indeed it must be slowing down because the kinetic energy decreases. So we could predict it was going to slow down here, and then we can see that it did indeed slow down because it has less kinetic energy because some of that energy has been converted into potential energy. It was moving to the left, though, and it still has kinetic energy, so it's still moving to the left. But since our slope is negative, our force is positive. So we're going to be moving in the left, the negative direction, with a force to the right in the positive direction, which means we're going to keep on slowing down. And indeed, we continue moving to the left, slowing down until we stop. And we can tell we stop when we get back to this position where our mechanical energy is equal to our potential energy. And so we can tell just by looking at the graph that if we start here, back to the first one. If we start here, we can figure out just from the shape of the graph that it has to move to the right until it gets to here, and then it has to turn around and go back here. We can tell it's going to be going faster at the bottom, slower at the top. And you'll notice, so if you just watch what it's doing, it just looks like it's rolling, like if this was like a marble, it's just rolling up and down the sides of the bowl, right? Like if this was, instead of a graph, like a dish, the marble it just looks like the point does what like a marble would do if it was just rolling up and down the sides of the dish. And conceptually, that can be a really good way to think about what's going on. And also it works because in the case of a bowl, it just actually is converting, if a marble's rolling around inside of a bowl, as it goes up the sides of the bowl, it's converting it into gravitational potential energy. And so this actually could be the potential energy graph for a physical bowl that a marble was rolling around in. Because at this point in the bowl, its height would determine how much gravitational potential energy it had. But this graph could also define like a mass spring system or something like that. And so you can conceptually, rather than being like, what's the slope? Is the slope positive or negative? Force is in the opposite direction. Which direction was it going? And like all of that mess, just imagine it's a marble in a bowl. And so if you release the marble from here, it just goes back and forth, gets faster down here, slower up here. And so if you release the marble from here, gets faster, 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 reaches the max speed, continues moving to the right, gets slower, slower, and slower until it gets back to the place where all of the energy is potential, and then it goes back. Gets faster, 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 fastest at the bottom, slower, slower, slower. So conceptually, rather than doing, like, it's true because of all the stuff we just talked about, but it's easier to think about it for a lot of people just as like a marble rolling back and forth in a bowl. Just a reminder, this curve shows all the theoretically possible potential energies. We can only actually get there if we've put enough mechanical energy in the system. And so this area underneath the mechanical energy curve is what defines the possible positions for our system. So I mentioned that at the beginning, but there's an actual slide here that talks about that. And then the only other thing is just the important relationships and equations. And again, this is just a repeat of stuff we already have or we intuitively know, but just to reiterate, kinetic energy is the mechanical energy minus the potential energy. So this is based on our definition of mechanical energy as kinetic energy plus potential energy. But since the two things we have on our graph are the mechanical energy and the potential energy, the way you combine those is you subtract them to figure out how much kinetic energy you have. So the further apart those lines are, the more kinetic energy you have, the faster you're going. And the force, again, is the opposite of the derivative of the potential with respect to the position, which means the direction of the force is the opposite, has the opposite sign as the sign of the slope. And yes, that's all true, and in theory, like for you could calculate that, but conceptually, it is generally just easier to think about it as an object rolling back and forth in a bowl to imagine what it's going to do. And your bowl could have all sorts of crazy shapes depending on what the potter did. Just like our graph could have different shapes. But just imagine as a marble rolling around in a bowl, and if and only if you actually need to get a numerical value for the force, worry about doing the derivative. Otherwise, just conceptually, it's easier to think about as something just rolling around in a dish to describe how quickly the system is going to be working. And even though a marble in a dish is not the same as a mass spring system, the model still tells us what we need to know. It tells us where the system will go and how fast it will be going. The mass spring system goes back and forth, right, left, right, left, right, left, getting fastest in the middle. The marble in the bowl goes right, left, right, left, right, left, always fastest in the middle.